Hello everyone, I'm Ankur Chemburkar and I will be presenting on behalf of my team consisting of me, Shuhong Lu and Andrew Feng. Our work, Discrete Diffusion for Post-Speech Gesture Synthesis, is our solution to the GENEA 2023 challenge. The task of speech-to-gesture synthesis, as you all know, is a non-deterministic task. This simply means that for a given speech, there could be multiple plausible actions gesticulated by a person. Previous deterministic regression models, such as language to pose and sequence to sequence, are just not able to learn this aspect of the task. And so we come to a probabilistic generative architecture. For the past couple of years, in almost all fields of generative AI, diffusion models have been giving exceptional and diverse results. When compared to autoregressive models, they are much more flexible. In addition to this, diffusion models are also adept at conditional generation. The discrete version of diffusion models operating in the latent space are able to combine these generative capabilities with really fast inference speed. Popular models such as DALI 2, Stable Diffusion, and Midjourney all utilize diffusion for the task of text to image synthesis. A recent work employed discrete diffusion with the help of a vector-quantized variational autoencoder for this task and showed promising results. Some samples from the mentioned VQ-diffusion paper are shown in the bottom right corner. Motivated by all this, we decided to utilize this method for the speech to gesture generation task. So now I will quickly give a brief overview of our model architecture and training method. The first stage is training the VQ-VAE to accurately reconstruct the gesture. The encoder first reduces the representation to the form of gesture snippets. The number of snippets is significantly less than the number of time steps in the gesture. We set the number of snippets to be one-fourth the original time steps. These snippets are then passed through the quantization function, which replaces the snippet with the nearest vector present in the latent codebook. Finally, these replaced snippets are then decoded back in an attempt to reconstruct the gesture. This stage 1 training is supervised with the help of an L2 reconstruction loss and an embedding loss, which stabilizes training and updates the codebook entries. Once trained, the VQ-VAE model can be fixed for the stage 2 or can also be fine tuned. We decided to keep it fixed. As a quick recap of how diffusion models work, there are two processes, the forward and reverse process. The forward process gradually corrupts the input representation with noise for a fixed number of steps till pure noise is obtained. The reverse process is where the model tries to learn the reverse function by iteratively denoising the representation. The conditional diffusion process can sometimes run into a problem known as the posterior issue, where during training it completely ignores the condition and just focuses on reconstructing the input based on the corrupt representation. This results in poor alignment between the input condition and the generation. This is tackled using classifier-free guidance, which is also something we make use of in our implementation. The discrete version that we use is similar to the continuous one and is inspired from the VQ diffusion work mentioned earlier. We use the mask and replace diffusion strategy, where instead of gradually noising the sample, we randomly replace the tokens with other tokens or a new mask token. These transition between tokens are governed by a fixed transition matrix. The forward step has a closed form solution, and hence we can go from the input sample directly to a random mask time step in a single jump. We also use the reparameterization trick where the model straight away predicts a denoise sample. During training, we first obtain the latent gesture tokens with the help of VQ-VAE. This is the input to our discrete diffusion. We jump from this input to a random time step and train the transformer model to predict the denoise sample with the help of the condition. This denoise sample is then again decoded by the VQ-VAE decoder to finally reconstruct the gesture. The training is supervised with the help of a KL divergence loss. In the inference stage, we start from the completely masked state and apply the model a fixed number of times to obtain a completely maskless representation. So here are the basic laws and metric graphs from our training. The main quantitative metric we used to evaluate the gestures was facet gesture distance or the FGD. For the VQVAE, we observe a uniform improvement over the 35,000 steps, which is around 120 epochs. We were able to obtain a final FGD of zero point 0.7, but this can definitely be improved with further training and more hyperparameter tuning. With our limited experiments, it was observed that the performance of stage 2 depends heavily on the stage 1 VQVA checkpoint. The model also starts overfitting at 12,000 steps mark. However, we do not observe any decrease in quality of the generated gestures as evident by the FGD curve. All the competing models were evaluated by the GENEA organizers. Our model SI does not perform exceptionally well or bad in these metrics, but just shows average performance, ranking in the middle. We could attribute this to a few reasons. Due to the timeline of the challenge and our efforts for developing and tuning the discrete diffusion model, we were not able to perform extensive experiments. For example, we were not able to experiment with what combinations of input conditions worked best and just stuck to using the main agent and interlocutor's audio for the experiments. Our generation also focuses only on producing the body and arm motions, ignoring the finger joints. So, what are the things we learned with this work? Firstly, the VQ-VAE is a very strong method for generating diverse gestures as it is essentially synthesizing a gesture by rearranging tokens from the original data distribution. However, getting good performance requires a lot of hyperparameter tuning. In our experiment, it was observed that slight variations in the hyperparameter resulted in significantly different performances. An unexpected observation was that the VQ-VAE checkpoint with the best FGT did not perform the best when incorporated in stage 2. The VQ-VAE overfitting could be a reason for this. And so we ended up using a VQ-VAE with FGT of 1 instead of zero point 0.7. The latent discrete diffusion approach also is much faster than previous approaches, and this enables fast training. Another surprising result observed was that overfitting during the stage 2 actually seemed to generate visually better looking gestures on both the validation and test datasets. After observing the final synthesized gestures, we also noticed a slight jittering artifact. We hypothesized that these issues were caused due to the discrete nature of the representation. Some sort of smoothing is necessary as a post processing step to improve the quality of the gestures. Finally, as a conclusion, we utilized a two-stage architecture that uses discrete diffusion on the latent dimension to generate diverse and condition-aligned gestures. We believe that this is a promising direction as it reduces inference times, does not hurt the generation capabilities as much when compared to utilizing continuous diffusion on the raw gestures directly. There are some obvious improvements we see in the future, which will certainly help this approach. Thank you all for your time.